Proportional relationships. Two families drive at constant speeds. Some data from their trips are shown in the tables below. All right, so here, what's the slope? Well, that's 70, and the slope here is also 70. What's the ratio of y to x for each family? Well, for family Z, that would be 70 to 1. Family A, it varies. If the data from both tables were graphed on the same coordinate plane, what would you notice? Well, here we have the ratio 70 to 1, except when time equals 0, as that's the same as slope. Here, it varies with each point, no relation to slope. The lines are parallel, but family Z goes through the origin. A proportional relationship is a relationship in which the ratios of related terms are equal. Some linear equations have a proportional relationship. Those that do are known as direct variation equations, which take the form y equals mx and pass through the origin, where b equals 0. Not all linear equations have proportional relationships, as we saw in the prior example, but those who do must cross the origin. When a linear equation has a proportional relationship, then the ratio of related terms is also the slope, as we saw with family Z.
The proportional relationship is expressed in the slope and the ratio of every y coordinate to every x coordinate, with the exception of the origin. Now, why would that be? Why is the proportional relationship not shown with the origin? Well, remember, the coordinates for the origin are 0, 0. So if we tried to have a ratio of 0 over 0, it's not a real number. Here is an example of a proportional relationship. Again, we have the graph. Now, the slope we have, if we go from one point to the other, is we're going to have a relationship of 3 over 2, because from point to point, every x and y coordinate, well, it's the same as your slope, which is 3 over 2. But it's also, if you took the ratio of every coordinate except the origin, you would get 3 over 2. So an example is you have the point 2/3. So y over x would be 3 over 2. Even if you took, let's take this point here is 4, 6. Well, 4 over 6 simplifies to 3 over 2. You can do that for any point on this line. So the equation of this line is y equals 3 over 2x. You can also see this in tables like we did with family A and Z before. Here it says, what is the proportional relationship in the table? So we need to look at the y over the x. So for this point, you would have 5 over 3. You would have 10 over 6, which again is 5 over 3. Or you would have 15 over 9, which again simplifies or reduces to 5 over 3. That's the proportional relationship, 5/3. So our equation is y equals 5/3 x.
Direct variation graphs can also be used to convert currencies. Remember the problem below. Convert 55 US dollars to South African Rand using the exchange rate of 1 US dollar equals 18.4 South African Rand. The equation to represent this scenario is y equals 18.4x. The graph showing this conversion rate is provided to the right. Reading the graph also allows one to find the solution. At 55 US dollars, here, the South African Rand is just above 1,000, 1,012 to be exact. Convert 40 British pounds to South African Rand using the exchange rate 1 British pound equals 23 South African Rand. The equation to represent this scenario is y equals 23x. The graph is shown to the right. At 40 British pounds, the value for the South African Rand is just above 900, 920 to be exact. Convert 35 euros to South African Rand using the exchange rate 1 euro equals 19 South African Rand. The equation to represent this scenario is y equals 19x. The graph is shown to the right. At 35 euros, The value for the South African rand is between 6 and 700, 665 to be exact. Variation describes the relationship between variables. We just learned about direct proportions, also known as direct variations. These proportions have 0, 0 as a solution and have a constant ratio. Inverse proportions, also called inverse variation, occurs when one value increases and the other decreases. With inverse variation, when one element increases, the other element decreases, or vice versa. When one element decreases, the other element increases. For example, as you pull on a rubber band to make it longer, the width of the band gets smaller. As you increase your amount of spending, you decrease the amount of money available to you. As you increase your altitude by hiking up a mountain, you will feel a decrease in the temperature. Using more mathematical vocabulary, inverse proportion is, for example, that when the temperature of the air varies inversely with the altitude, written as temperature equals K over altitude. Graphically, this could look something like this. As one variable increases, like on the x-axis, the other variable on the y-axis decreases. The table below compares direct and inverse proportions side by side so that you can see the similarities and differences.